Hi everyone. So I'm going to be making an example video for center of mass calculations and moment of inertia calculations, the types that we're going to see in this chapter. This textbook starts in this section talking about moment of inertia because it's needed to be able to calculate rotational motion for a rigid body. In the textbook, you have this table, which you should see up on your screen now. This is the center of mass and moment of inertia for regular geometric shapes, and these are the ones that you're likely to see: spheres, cylinders, cones, plates, rods, rings, discs. Those are the things that they make up their shapes out of, and it's true most things can be thought of as being comprised of shapes like this. The example problem I want to focus on is this one. The pendulum consists of a 3 kilogram slender rod and a 5 kilogram thin plate. Determine the location of the center of mass, then calculate the moment of inertia of the pendulum about an axis perpendicular to the page passing through G. First of all, before I get into this too much, an axis perpendicular to the page, that's the case for every 2D problem in general. We're always talking about an axis perpendicular to the page. So don't read into that too much. That is always the case. As a result, we kind of want to be looking at our previous image, this one here, and thinking about these different objects. So first of all, they say a slender rod. For the slender rod, that's this. Really trying to slender rod. And an axis perpendicular to the page is either the x-axis or the y-axis here. We're talking about those. Ix and Iy go through the center of mass of the object, and you can see that the formula for those is given here. And this formula I actually used in my previous video. So the I we want to use is 1/12 ml squared. Then the thin plate, we want to find the moment of inertia of it. Its moment of inertia about its center of mass is given here. As far as the moment of inertia about an axis perpendicular to the page, that is the z-axis out of the plate. And we can see that Iz is equal to 1/12 m a squared plus b squared. So we'll be using those formulas in this calculation. But again, I don't want to know the moment of inertia of these shapes about their own centroids, that point and that point. I want to know their moments of inertia through the overall center of mass at G. But I don't know where G is. So step one is find the center of mass. Okay? Again, I'm going to build this in a little table because I find it convenient. In this table, I'm going to be focusing on the two objects that comprise this composite object. The two objects are the rod and the plate. For object 1, we have its mass. The mass is 3 kilograms. And, well, let me not include the kilogram here. I will go ahead and just say m is in kilograms. So this is 3, this is 5. For object 1, its y-bar location. Well, first of all, I need to select a centroid. Sorry, not a centroid. I need to select an origin. I'm going to use their point O, which is a bit odd, simply because it's above everything. I usually like to pick the point at the bottom, but I notice that they are asking for y-bar, this distance, so I'm going to measure it from that origin at the top because it will give me that distance. I'm going to say that downward is positive for the sake of this calculation, so I don't have to deal with negative numbers, although it doesn't really matter. Where is y-bar of shape 1? Where is its centroid location? Well, it's a 2 meter long rod and it's uniform, so it's going to be in the middle, 1 meter down. And then for the plate, again, measured from here. Do not measure from its top. That's inappropriate. We're measuring from the origin. The centroid of the plate is 2 meters down and then another 1/4 of a meter down to get to the center of the plate. So 2.25. The next column of the table will be for x bar, also measured in meters, but I don't know about you, I'm not interested in x bar for this problem. It's pretty clear that because both objects are symmetric and their center of masses are in the middle, that the overall center of mass is going to be in the middle in the x direction. The center of mass is certainly on this line. So I'm not really going to worry about the x. I'm just not so concerned about it. But the overall centroid location, rather center of mass location, is equal to the sum of mi bar I divided by the total mass. Oh, that was a good m. Here we go. Center of mass. And this is equal to 3 times 1 plus 5 times 2.25 divided by 8, which is equal to... Did I bring a calculator with me today? Yes, I did. Okay. 3 times 1 plus 5 times 2.25 divided by 8, which is the total mass, is 1.781 meters, measured from the top to the bottom. All right. Now, I need to find the moment of inertia of each shape. The moment of inertia of shape 1, first I'm going to find its moment of inertia about its own centroid. The moment of inertia of the slender rod about this point in the middle. In my notes, I called this point G1. I'm not going to bother calling it that today, but for a slender rod, the formula for the moment of inertia about its centroid is 1/12 times its mass times its length squared. And then I've got to use the parallel axis theorem to find the moment of inertia about G. That is the mass times the distance, that is this distance, squared. The distance between where this formula was valid, which is its own center of mass, and where you want to know it, which is the overall center of mass at G. That distance is, well, this is 1.781 meters down, and the original center of mass is 1 meter down, so 1.781 minus 1, and that is squared. This is equal to 1/12 times 3 times 2 squared plus 3 times 0.781 squared is 2.831 kilogram meters squared. Cool. Now I need to find the moment of inertia of shape 2. That's equal to 1/12 its mass, which is 5 kilograms. And the formula for a thin plate is a squared plus b squared, where a and b are the side lengths. So this is going to be 0.5 squared plus 1 squared. And then I've got to use the parallel axis theorem. I need to add the mass times the distance between their centers of mass. So that distance there is what I'll call D2. This G is 1.781 meters down, and this point is 2.25 meters down. So I'm going to go ahead and just do 2.25 minus 1.781 squared, and that's going to be equal to 1/12 times 5 times 0.5 squared plus 1 squared plus 5 times 2.25 minus 1.781 squared is equal to 1.619 kilogram meters squared. I'm curious to look at this to make sure I didn't make any errors, just simply because this object is more massive, yet its moment of inertia is smaller. Notice that, right? This number being smaller than this one. If I were to look at these calculations, it wouldn't be too much of a surprise. The reason is that the distance between this term in particular is quite a bit larger for I1 than it is for I2. I still am curious, so I'm going to look through my calculation and double check it. It all seems to be correct. So it's worth noting that this term is also bigger than this term, I suspect, simply because this 2 squared is quite a bit larger than this term. Okay, I'm going to erase all these underlines that I've added because I don't need them. How many are there? Jeez. Now I'm worried I erased too much. Okay, well, it's time for the eraser tool. Okay. Looks like I'm missing my unit, kilogram meters squared. Okay, so with that said, the total moment of inertia about G for this shape is equal to just the sum of I1 and I2, and that's equal to 2.831 plus 1.619, which is equal to 4.451 kilogram meters squared. It's worth noting that for this calculation, I would do this all at once. As far as the moments of inertia are concerned, I would put this in one line and evaluate it in my calculator all at once, rather than calculating the moments of inertia of each shape separately. I would find the centroid location as its own calculation up above. So for me, and one familiar with this calculation, this would be kind of two basic steps. One, find the centroid. Two, find the moment of inertia. All right, well, that's it for this example. I am curious to look at other examples. Oops, not that. Let's see. So I'm going to be focused on this one here. Let me bring this in real quick. If you're wondering why I didn't do this in advance, me too. But I'd rather not start the video over or put in a big pause, so we'll just do it like this. Note shelf. Let's make a new page and add this new photo. There are two problems here. Determine the moment of inertia of the wheel about an axis which is perpendicular to the page and passes through the center of mass G. The material has a specific weight, gamma equals 90 pound per cubic feet. This is a bit of a bummer. This problem has a pretty regular shape, but instead of giving us the mass of each piece, they are telling us the density of the object, which adds a little bit of complication to the calculation, but not too much. In this situation, the mass of the object is going to be determined, or I should say the weight, I suppose. The weight of the object is going to be determined by taking its volume multiplied by the density. So I've got to consider the volume as well. Okay, so first of all, do we need to talk about center of mass? I don't think so. This object is completely symmetrical in the circular direction, and they've identified that. They put G right in the center. So that's the first thing. Should be pretty straightforward. So we're just calculating the moment of inertia. I am going to calculate the overall moment of inertia with these three different shapes. I'm going to take the little holes as a shape. I'm going to take the central disk as a shape, and I'm going to take the outer ring as a shape. Let's see if they actually let me do that, now that I think of it. I'm curious to check. The reason I'm curious is that the formulas we have at our disposal are these, and this is for a thin ring. The question I'm concerned with is, do they tell me the thickness of the thin ring? And they sure do. So I should probably consider its actual thickness. So I will take a slightly different approach. So let me revise my opinion of my shapes. I'm going to just do a solid disk the entire size of the shape. So that is a solid disk that is 1 foot thick and has a diameter of a radius of 2.5 feet. That's going to be shape 1. So shape 1 is the overall shape. Let's find the moment of inertia of shape 1. So the moment of inertia, let's say this first of all. Shape 1 is a disk 1 foot thick, what is it, 2.5 feet radius. Fortunately, they give me the formula for the moment of inertia about this perpendicular axis, the z-axis. It's, oh, whoops, wrong one. 1/2 mr squared. But I should recognize immediately, I don't actually know the mass. The moment of inertia, yes, is equal to 1/2 m times 2.5 feet squared, but I don't know the mass, so I'm going to need to calculate the mass. To calculate the mass, I need to find the volume. The mass of shape 1 is equal to the volume of shape 1, which is pi times 2.5 feet squared, times the thickness, which is 1 foot. And then times the density, which is 90 pounds mass per cubic foot. I'm going to go ahead and use pound mass as my unit for this problem. Please note I would need to convert to slugs before the end if I was going to use this in a dynamics calculation, but I'm just going to go ahead and use pound mass and convert at the very end. This is equal to pi times 2.5 squared times 90, which is 1767 we'll leave it. This is going to be in pounds mass, which makes the moment of inertia, I1, equal to 1/2 times that times 2.5 squared equals 5522 pound mass foot squared, which is equal to, converting to slugs, 171.5 slug feet squared. That is not the moment of inertia of the overall shape, just of shape 1. And now I need to cut stuff away from it. The first thing I'm going to cut away from it is this. There are 2 of them, and they're identical. They have identical moments of inertia. They are thin discs. They have a thickness of, well, let's see. This thickness is going to be, gosh, let's see, it's 1 foot overall minus 0.25 feet, which is the center bit. That's equal to 0.75 feet. And then each of them have half that much, which is 0.375 feet, or 3/8 of a foot. Great. So this is the overall thickness of each of these plates. So I am going to calculate the mass of those disc holes, I guess I'll call them. I'll call this shape 2, and there are 2 of them. I'm going to just do this for one of them. So the mass of that disc is pi times its radius, which is 2 feet, times its thickness, which is 0.375 feet, times the density of the shape, which is, well, technically this is a negative because it's a hole, but I'm just going to calculate the mass that would have been there and then just subtract it, times 90 pounds mass per cubic foot is equal to pi times 2 times 0.375 times 90. All right, well, I took a little break there for a question from a student, but I'm back, and fortunately, when checking to see what I had been doing and where I had left off, I found a mistake in what I was just calculating. This is supposed to be pi times r squared, times the thickness times the density. So this should be pi times 2 feet squared times 0.375. So we just need to fix that. Make sure that squared was also in my previous calculation, but it was. So, all right, times 90. This is going to be 424.1 pounds mass. So that seems pretty reasonable considering the overall object had a mass this large. I think that this number seems reasonable. Okay, so that's the mass. And the moment of inertia for a disk of that sort, I2, is equal to 1/2 mr squared. The mass is 424.1 pounds mass. And the r there is 2 feet. Square that. This is equal to 848.2 pounds mass. So it's worth considering how this is going to change or how I'm going to use this number as I move along. And many of you are probably considering that, aren't there 2 of them? Don't you need to double this? Isn't a whole? Don't you need to subtract it? Yes to all of those things. I'm just going to handle that later. All right, the next thing I'm going to worry about is this, come on, is this little hole here. There's 4 of them. They are circular holes. To find the moments of inertia about the center of mass, I need to find their individual moments of inertia and use the parallel axis theorem to move them to the center of the circle. So I'm going to call this shape 3. This, I kind of wish I'd done that for the other one. Oh well, the small holes are shape 3. Their moments of inertia, well, first of all, let's calculate their mass. Let's undo that. The mass for shape 3 is equal to, once again, just their volume times their density. They are pi times 0.25 feet squared times their thickness, which is 0.25 feet also, times their density, which is 90 pounds mass per cubic foot. And that's equal to, let's see, pi times 0.25 squared times 0.25 times 90 is equal to 4.418 pounds mass. And that means that their moment of inertia is equal to 1/2 mr squared, which is 4.418 pounds mass, times their radius, which is 0.25 feet. That's squared. Then I have to add the parallel axis theorem term, which is their mass, 4.418 pounds mass, times the distance between their center and the overall center, which is this distance here, 1 foot. So 1 foot squared. This is equal to, if I calculate that out, 1/2 times 4.418 times 0.25 squared plus 4.418 times 1 squared is equal to 4.456 pounds mass. This is pound mass feet squared. As I was doing this calculation, I noticed a couple of not really big mistakes, but mistakes nonetheless on my previous calculations. This is a moment of inertia calculation. As such, it's pounds mass feet squared, so I need to correct the unit there. That's a pound mass feet squared. Additionally, up here when I calculated the moment of inertia, I converted it to slugs, which I probably should do for the others as well, so I will do those conversions. This conversion, 848.2, converted to slugs is 26.3 slug feet squared, and this is 0.141 slug feet squared. The overall moment of inertia of this shape about its center of gravity is equal to I1 minus 2 times I2 minus 4 times I3. And the reason is I2 is a whole, so it's subtracted, and there are 2 of them, so I subtract it twice. And I3 is also a whole, so it is subtracted, and there are 4 of them, so I will subtract it 4 times. To do this calculation, I'm simply going to plug in these numbers. So I1 is 171, I know this is my calculator somewhere, minus 2 times 26.3 minus 4 times 141. This is 118.3 pounds mass foot squared. Oh, that's not pounds mass, is it? That's slugs. Let's correct that. What a terrible way to end a video. Slug feet squared. There we go. This calculation is necessary if we're going to figure out anything about the rotational dynamics of this object. So here's our final answer. I'm hoping that it's right. This video is done raw. I don't have a solution prepared in advance, so if you find any errors in it, feel free to send them my way and I will make a correction, or maybe just redo the whole video. All right, so we have these 2 example problems. They are things that you'll find in section 17.2 of Hibbler's Dynamics textbook, and they are necessary steps for all future sections of this chapter as well. Alpha depends on the moment of inertia about the center of gravity, so we need to know how to calculate it for a general object. All right, well, that'll be that. Look for example problems on translational and rotational motion in the future.